hope you weren't tired of the topic before, but we're going to be talking about message aggregation again. Simple paper here. This time we're just looking at the effects of aggregation on not speed up or throughput or anything like that, but just on power savings. So there we go. So basically, as everyone here has noticed already, Moore's law has, it says here it's slowed, it's basically dead. And energy efficiency is increasingly vital to consider for center operations and for research bottom lines. And in particular, part of that is that data movement is increasingly an expensive point of contention. And this is especially true for the also familiar PGAS environments that I was talking about earlier, precisely for the same reasons. A lot of need to, with that model, there's a lot of transfers of various sizes. And so this, this time we're going to be focusing on how can aggregation, as we've discussed before, be able to improve upon the power constraints of the system a bit. And so again, yes, increasingly we're facing power walls limiting our use instead of just compute resources. And there's a lot of potential that we saw before for kind of in this particular space, in this model, for trying to kind of attack this problem. So the thinking here is that maybe we can get two birds with one stone and free up a lot of those compute resources for something that they're maybe a lot better spent on than simply moving data from point A to point B. So there's a few key questions that we're focused on for this. The first is how much energy can be saved with aggregation compared to traditional AGP or atomic get-put models. Second question is, how does the performance improvement correlate with energy savings? Ultimately, we are concerned with both. And the last question is, what are the effects of message aggregation on CPU and memory power utilization? So this looks a lot darker up on here. So basically, this is what we call a marketing slide. My supercomputer beat up your supercomputer. This was like before that we ran all these tests on the Frontier system. It's got 9,408 nodes, and we will be using 2 of them. And so in particular, what we saw with the previous presentation is that we basically have already been able to determine, at least on this system, that the performance profile is more or less stable across increasing numbers of process counts. So we, between that and constraints with analysis tools, we just stuck to 2 and then did all of our analysis from there. Specifically, we used HPM to get some performance counters from the system on energy and power for breaking it down with the CPU and memory that we were interested in. And we used for analysis and visualization ScoreP and Vampire. Additionally, this was also using the latest Cray OpenSHMEM X at the time, which was 11.7. And again, we're going back to those same bale applications, although we're going to be running a much larger range of them, 5 total. So histogram was the one that we saw before. Index gather is similar to histogram, except instead of sending data a bunch of random places, you're retrieving it from a bunch of random places. We have sparse matrix transpose, triangle counting in directed graphs, and topological sorting. So for this first one, we're looking just at the time improvement. So not really big surprises here. I should also clarify, I did give a talk just recently about the whole aggregation context thing. For the purposes of this, we're actually just focusing on the conveyor model. So this is not, I gave a talk recently on that, but this is not about the context. So this is only about non-aggregated versus conveyor aggregated approaches. And here we see the time improvements across all the different applications that we have, but we want to know, does this translate to power savings as well? So we can see that bottom line, energy savings do increase quite a lot. The sparse matrix in particular received 41 times memory improvement. So we're getting, orders of magnitude of performance increase, and also orders of magnitude less power energy use, which is nice. 32 times for increase for triangle counting, and topological sort is actually by far the most difficult and complicated application in the suite. So it was rather nice to be able to see that we also were able to get 39 times improvement for that as well. And for the most part, energy savings continue to increase with increasing intranode process density. So as we increase the PPN count.
This side and the previous side were almost identical.
Yes, there is a very close correlation. Yes, and that wasn't a guarantee, but that's why we're running this stuff, so we can know these things. And in fact, that's exactly what this was looking at. So thanks for pointing it out. So here we're looking at the ratio of the increase of time versus the increase in energy. So if it's exactly 1, they increased it at the exact same rate. If it's above 1, then the time savings were greater than the energy savings, and then the other way around for if it's below 1. So we see some interesting different behaviors from there. A lot of them still kind of hover, reasonably close around 1, but some applications like histogram and index gather, it says triangle counting. I think that was a typo here. But some applications exhibited particularly peculiar behavior at low process counts, where we could see in the case of histogram, the energy savings were far greater, the time savings being far greater for index gather. Again, that's basically remote sending versus remote receiving, and that's an interesting thing to see. But now we'd like to be able to look at a bit of a breakdown of the actual power consumption. So this is histogram specifically, looking at 16 ppn. Again, 2 nodes, 16 ppn. What we're looking at here, if we break it down, we see there's some clear phases. So first of all, this is running everything in one go. So it does the non-aggregated run, and then it resets, and in the same run, it does the aggregated one. And so when we look at the breakdown at the top here, the sort of reddish section, that's basically just initialization of all the memory and structures. All the green, that's what we're looking at for the non-aggregated approach, the AGP. And then the purple is the aggregated approach with conveyors. The AGP uses constant, and the below we see the breakdown between not just power use, but specifically CPU power use versus memory power use. If you can't see it in the back, the middle one is CPU power, the bottom is memory. So the AGP we saw used a rather constant 77 watts for the CPU and 89 watts for the memory versus 103 and 91 for conveyors. But despite there being marked power increase for conveyors, because of how much faster it's able to complete, the total energy use, as we saw before, still goes way down. So higher power, lower energy.
I suggest that the middle diagram be called the Vivek submarine.
All right. So now we're looking at the average power ratio. That's also comparing aggregation over AGP. And we see that the average power consumption is usually higher than AGP, as we saw before, which is not surprising. We pretty much expect it, except for the lower power counts. I'm sorry, lower process counts, like we saw before. When we see some of that unusual behavior, it does actually very rarely switch over to going in the other direction. But I guess don't run across 6,000 nodes with only one process per node, and you'll be fine. Topological sort and histogram. I don't know what he was referring to that one, that point for, but basically, as we use more cores, we tend to use more power, but gain more savings. That's the takeaway. Okay, so other insights. I think I'm good on time. Energy savings can be potentially greater at lower process counts, where the memory use is actually dominating. But as we increase the power process counts, what we're basically doing is we're moving the constraint on power from memory to the CPU, and that's when we start seeing the huge savings really start to kick in. There's a sort of a trade-off point where we kind of equalize on that, and then it just keeps getting better. Beyond that point, the conveyor aggregation strategies can help maintain that balance where we want it to be. Again, freeing up the CPU for other tasks, but aside from data movement. I think what right. The 8 to 16 was basically what was the determination for roughly where that milestone is. Where before that, for saving energy, you might want to not aggregate, and beyond that, you benefit the most from aggregating. So, in conclusion, obviously, there is a lot of just like with execution time, there's a lot of potential for lowering system power, compute center power bills from using aggregation, and achieving. We achieved up to 41 times improvement for some of these applications by doing so, even at the cost of greater power use, and again, like I also said before, there's the trade-off between memory and power. Memory and CPU, which is basically what drives all of this. Any questions? If you've tried doing full traces of like 2,000 nodes or whatever, you'd know that you probably don't want to actually do that.
And does that vary by the size of the application? Meaning that if you had a larger application, that maybe more nodes would be useful? Or does that matter?
Well, the more nodes you have, or the bigger the problem size, or just generally the longer you're running, in terms of core hours, that's going to make a much bigger trace. So you could easily start talking about, here's my terabyte trace or whatever. But to reemphasize, this only came after a lot of existing testing, some of which you saw before, that basically already showed us that the profile of behavior that we were interested in wasn't really changing significantly by using those higher node counts. So we focused instead on what was more tractable.
Right, let's thank the speaker again. Oh yeah.